So let's move on to the relationship between torque and angular acceleration. So everything, again, as we said, we've seen linear acceleration. Let's see what happens when we take into account objects moving then in rotation or about some rotational axis. When a rigid object is acted on by a net torque, it undergoes angular acceleration. The angular acceleration is directly proportional to the net torque. So if we consider a mass m connected to a very light rod of length r, let's develop the relationship. So again, a very light rod tells us we're going to discount it. So we start off with our linear relationship. That's what the T here, force tangential. And you can see here we've got acceleration tangential following the, not following the arc, but following a trajectory off of the arc if the object were to loosen itself. So we have force tangential equal to mass times acceleration, in this case tangential. So if we bring in the radius, okay, that's the radius of the rod, so let's multiply both sides by the radius. So because we want radius to be in the mix. So force tangential times the radius, which is really force times distance, is equal to mass times the radius times the acceleration tangential. And recall, in the last chapter, we saw that acceleration tangential, our linear term, had a conversion factor that said it was equal to the radius times the acceleration, in this case, the angular acceleration. So now, force tangential times the radius is equal to mass times the radius, and we are going to substitute for acceleration tangential this term radius acceleration angular. And so now we get mass radius squared times the acceleration. Again, sometimes we do these manipulations and we add these terms because we have a goal in mind. We're looking to define something that we can use to help us solve other types of problems. So this definition then will allow us to define the torque relationship. So now we have force tangential times the radius, which we've already defined as torque. So take it one more step, then torque, tau, must equal mass times radius squared times the angular acceleration. So this constant of proportionality, mass times radius squared, is something now we call the moment of inertia of the mass. And the moment of inertia, we're going to find out, is based on the geometry of the mass itself, of the object. So the total torque on a disk is given by the sum of the individual torques on all particles. Okay, so if we look at a disk, because a disk is rigid, the angular acceleration is not involved in the sum. So what we're going to do is we're going to say, okay, let's sum all of the torque values, and we are going to extract out the angular acceleration. So now it becomes the sum of all the masses at their given radiuses squared. So the sum mr squared then equals, just like we saw before when we did our center of gravity relationship, the first mass, radius 1 squared. Second mass, radius 2 squared, etc., etc. So the quantity is called the moment of inertia of the whole body and is given by the letter I. So we use the capital letter I to define this term, summation of mass times radius squared. Okay, it has units that are SI units, and those units are kilograms times meters squared. And if we look at the relationship, we can see mass is kilograms, radius is in meters, so kilograms times meters squared. So if we put that back into the first relationship, now we have the summation of all of the torques is equal to the summation of all of the mass times radius squared times the acceleration, and we substitute now, for simplicity, the letter I. So again, we have to look at, we've got a a line here that we move along, okay? So it moves along based on SI units all the way out to the simplistic term I. The angular acceleration of an object then is proportional to the net torque acting on it. So the summation of all the torques equal to the moment of inertia times the angular acceleration has a counterpart, okay? Its rotational counterpart to Newton's second law then, as we saw, was the summation of the forces, of all the forces, is equal to the mass times the acceleration. So we have like things in different worlds. The linear world, the Cartesian world, whatever you want to call it, the rectangular world. Now in the polar world or the rotational world, we have another set. So as I said, the value of I is based upon the geometry. What does the object look like that we're trying to determine the torque or the moments of inertia for a given problem? So we have to be careful when we're solving problems that we choose the right value for I, the moment of inertia, based upon the geometry. You can see here for a hoop or a thin cylindrical cell, the moment of inertia is equal to the mass times the radius squared, just as we identified it. If, though, it's a solid cylinder, notice everything here has been filled in. If it's a solid cylinder or a disk, it's equal to 1/2 the mass times the radius squared. If we turn this solid cylinder disk into a long, thin rod with a rotational axis through the center of the rod, okay, pay attention to that, we have the moment of inertia equal to 1/12 of the mass times the length squared. Now, if we move to a solid sphere, the moment of inertia is 2/5 of the mass times the radius squared. If we have a hollow sphere, okay, a thin spherical shell, I is equal to 2/3 the mass times the radius squared. And if we change the pivot point on the long, thin rod, making the rotation of axis through one end, it's equal to 1/3 the mass times the length squared. So in every case, it's geometry, physical geometry dependent. So you'll have to pay attention to that when you are solving these types of problems. Choose the wrong one, you're going to get the wrong answer. Okay, rotational kinetic energy. So now we're moving back to our terms. Remember we had kinetic energy 1/2 mv squared, potential energy mgy. Okay, so we're going to focus on the 1/2 mv squared relationship for kinetic energy. So a body rotating about some axis with an angular speed omega has a rotational kinetic energy given by 1/2 the moment of inertia omega squared. Okay, so let's look at the relationships here. The kinetic energy in a rotational body is equal to the summation of all of the masses, 1/2 mv squared, and in this case, we're going to call the velocity r omega. Again, we saw this in the previous section where we developed this term. So again, we have a conversion relationship between linear and angular. So the kinetic energy in a rotational body is equal to the summation of all of the masses times the radius at some distance times omega squared, okay? Because we substituted r omega for v squared then became r squared omega squared. So 1/2 the mass, r squared omega squared. Again, we're going to factor out the angular speed, omega squared, so that we can come up with our value of I. So the kinetic energy rotational is equal to 1/2 the summation of all of the masses times the radius squared within a body times omega squared. So kinetic energy rotational then is equal to 1/2. Let's make the substitution using I, 1/2 I omega squared, where I is equal to the sum of all of the masses times the radius squared. And we call this then the moment of inertia of the body. Okay, so for conservation of mechanical energy, just like in the last sections where we brought this in, where we used friction and where we use a spring, now for a rotational body, we can substitute, or we can add into the potpourri, if you will, the term for conservation of mechanical energy, where we're dealing with a rotating body. And there it is right in the middle. So kinetic energy tangential plus kinetic energy rotational plus potential energy of gravity, all of these on the initial side. We do the same thing on the right side. All of these are on the final side. Only true, though, if we ignore dissipative forces like friction. So we leave that out of the mix, okay? So this allows us to sum problems that look very complex, that have things move linearly as well as rotationally, as well as having potential energy to solve for different functions. And we're going to see that as we solve some problems. So let's try one here. We've got a ball with a mass m and a radius r, and it starts from rest 2 meters above the ground and rolls down a 30-degree slope. What is the linear speed of the ball when it leaves the incline, assuming the ball rolls without slipping? So we're going to say the ball maintains positive traction on this slope, hits the bottom here, attains some maximum velocity, and goes rolling off the screen. So let's start with the relationship we just defined, conservation of energy, and we're going to let the potential energy equal, again, potential energy of gravity. So there's our relationship, just as we designed it previously. And we're going to say then that the kinetic energy tangential initial equals the kinetic energy rotational initial is 0, because they told us the ball started at rest. So all of these terms, both of them start at 0. The other side, at the finish line, the potential energy gravity, once we know it has expended all of its energy moving through that 2 meters of height, once it hits the bottom, the final potential energy of gravity is equal to 0. So we've simplified the terms. We've taken lots of them out. We've taken 1, 2, 3 of the terms out. So 0 plus the mass times the gravity times the height at 2 meters is equal to 1/2 the mass times the velocity squared at the finish line plus 1/2 2/5 meters or mass times the radius squared times omega squared. Again, remember, we have to use the correct I. The correct I for this case is a solid sphere, 2/5 mass times radius squared, okay, and plus 0. So if we say then the ball rolls without slipping, then R omega is equal to velocity. The no slip condition then is applied. So since we are looking to solve for the speed here, let's start moving terms around, okay? So first off, I'm going to do is I'm going to solve for the mass times the gravity times the height, and that's going to give me 1/2 mv squared plus 1/5 mass times velocity squared is equal to 5/10 mass times velocity squared plus 2/10 mass times velocity squared. What did I do here? I created a common denominator. 2 and 5 gives me a common denominator of 10. So MGH is equal to, okay, because there's our MGH on the left side here, 7/10 mass times velocity squared. Do we see anything common in both sides of the relationship? The mass. The mass of the sphere doesn't change. So get rid of it. Throw it away. So what we're left with then is gravity times height is equal to 7/10 of the velocity squared. So let's move things around. Let's move this velocity squared to the left side of the equation, everything else to the right side of the equation. So when we do that, we've inverted. So we've got 10/7 now times the gravity force and the height. So when I take the square root then of that value, I get the square root of 10/7 gravity times height is equal to, now let's start dropping numbers in. 10 times 9.8 meters per second squared times 2 meters divided by 7. Once I run that through and take the square root, the velocity of the sphere, once it hits the bottom of the ramp, has a initial or a final velocity of 5.29, or about 5.3 meters per second. Okay, So before we move on to something a little more complex that has lots of moving parts in here, let's go ahead and stop and take a break.